Good evening, everyone. Welcome back to NPTEL live session. This is for week 4, and today also we'll be talking about the lectures that have been covered in week 4, that is lecture 16 to 20th. And at the end, we will be solving some problems. If there is any question or doubt from the previous sessions, please let me know before we start the session, and we will wait for a few more minutes for others to join. Thank you so much for joining. Before other people join, I would just mention that what are the topics that we're going to cover today. I hope my voice is audible to everybody. If there is any problem, please let me know. So the topics that we are going to cover today. So last lecture, we ended up having the preparation methods and how we have the selectivity towards the CP ligand, the substituted CP ligand, and what are the different bonding properties of CP ligand is there. And today we'll be looking into the reactivity of those complexes. Reactivity of transition metal. This is TM, cyclopentadienyl. Carbonyl complexes, meaning that besides CP, we will be having carbonyl ligands as well. It's just not the sandwich compound. It is besides the CP group, we have other ligands also. So we'll be looking into the reactivity of those systems. Followed by that, we will be introducing the cyclopentadienyl metal nitrosyl complexes. So nitrosyl is another type of ligand which can donate electrons in two different ways. We'll be talking in full details in later slides. And followed by that, their preparation, their preparation, their reactivity, and their bond distances and angles. Everything we'll be covering today. Followed by that, the third part that we will be talking today is transition metal based, transition metal cyclopentadienyl hydride complexes. So earlier we have seen the carbonyl complexes, then nitrosyl complexes, and another ligand is hydride. So we'll be looking into that into consideration. And followed by that, it would be same transition metal, CP and X, which is a halide. Halogen would be introduced, and those complexes we'll be studying today. So this is it, what we will be talking about today. And at the end, we'll be taking the problem session. Great. Okay, so what we ended up in our last session, just to give you a brief that what we have seen so far. So we were talking about the first topic that we are going to talk about again is cyclopentadienyl metal carbonyl complexes and how they look like. Say, for example, you have a manganese complex which is bound with your CP group. It can be CP, it can be substituted cyclopentadienyl, and other ligands are carbonyl. So this is one type of cyclopentadienyl metal carbonyl complex, and these are called as half sandwich complexes. This we have already discussed, because it is having at one side it is having a CP group, and the other side there is another group which is carbonyl. It could be nitrosyl also, it could be hydride also, and those complexes are known as half sandwich complexes because they are not fully sandwiched between the two CP rings. And we saw certain reactivity of those complexes at the end of our last session. So for example, when we are taking we are having CP, Fe, and carbonyl groups as a dimer, when it is being treated with sodium amalgam, which will do the reduction. Therefore, a charge, a minus charge, would occur on your iron center and CO whole twice. Since minus charge is there, now we are treating it with CH3I, meaning CH3 would be having a positive charge and iodine is having negative charge. Since it is having a negative, it would attack onto your methyl group, and therefore it would be having CP, Fe, CO whole 2, and CH3, and your iodine would bind with the sodium, making a sodium iodide. So this is the way where we have complexes both with the carbonyl increasing or decreasing the electron density onto the metal center. You're reducing it because you need to provide the electrons, as in when you are having a pi acceptor ligands already, say for example carbonyl, it would reduce the electron density onto the metal center, and for making it to react with the electrophile, you need to provide more electron density onto that. That's why we are giving a sodium amalgam, which would do the reduction of your metal center iron, making it from iron 1 to iron 0 to in this particular state to having a minus charge onto it. So after that, when it is having a CH3I, it would give you a positive charge on CH3, and then minus iron would attack onto your CH3, giving you a product. So this is of your interest. Moving ahead with our today's session, where we are going to see further reactivity of these complexes with, first of all, dihalogens. So I'm not going to redefine the title of this. So we are continuing with reaction with dihalogen. So what we meant is we have a similar complex, which is CP iron. For that, okay. CP bound with iron, having carbonyl group, which is a dimer, and it is now being reacted with X2. X could be your bromine, your iodine. Now, when we have a Br bonded Br and iodine bonded iodine, it would undergo a homolytic cleavage, and it would form your two molecules of CP, iron, CO whole 2, and X would come into the picture. When we have a halide already bound with this particular system, and now I'm treating it with AlX3, which is a Lewis acid, and in presence of carbonyl group, it would release the halide group, because AlX3 is Lewis acid and it can easily take your another halide group, making an AlX4 negative, and carbonyl can come into picture. Now, there is a point where we need to understand that halides are one electron donor, which is making a giving a one electron to the metal center, whereas carbonyl will give you a two electron center. And when you're introducing a two electron center, you need to balance out the charge by keeping a positive charge onto your whole system. Ultimately, we will end up having CP, iron, CO whole 3 with a positive charge, and AlX4 minus would be out, because you have introduced two electron species and you are going to replace it with one electron. So you have to balance out the charge by giving a positive charge onto your whole coordination sphere. So the highlighting and the note over here is we have CCl4 and PHCH2Cl, which can act as halogen source under the photochemical conditions. So if these reagents are also there, then also you have a possibility of getting a chloride or halogen into your system under the photochemical conditions. You need to provide a light source over there to let this reaction to happen. So this was one such reaction where we have seen, like, when it is being treated with uh, Lewis acids, how it reacts, and when it is being treated with halogens, how it reacts. And whenever we have a possibility of replacing a halide with the carbonyl, how the positive charge comes onto your coordination sphere. So moving ahead, we like in case of ferrocene, we have another complexes also. So we can write like this way: like in ferrocene, we have seen that it easily undergo electrophilic substitution reaction, which means that it's just like your benzene systems. When you have more electron density onto your system, that would attack onto your electrophile, giving you a desired product. So electrophilic substitution reactions. Because of the CP groups provide more electron density to your metal center, and that makes it highly electronically rich, which can attack onto the electrophile. Similarly, looking into that one, we have CP vanadium carbonyl 4, CP manganese carbonyl 3, and CP rhenium carbonyl 3. So these also undergo electrophilic substitution reactions like that of ferrocene. Taking one example, when uh, we are going to see the substitution of carbonyl group. So when we have a half sandwich compound, where carbonyl is a ligand which is bound with the metal center, can it be substituted with some other ligands? So we can see that if you are taking an example of manganese bound with Cp with 3 carbonyl groups, you can even count the electron density, total valence electrons. Cp will give you 5 electron, manganese is going to give you 7, which is already 12, and then you have 6 coming from 3 COs, meaning it is 18 valence electron. Right? Now you are introducing another ligand. This ligand can be your phosphate group. This can be your olefin, etc. So when you are treating with phosphine or olefin, your biggest that should also be a 2 electron donor. You should mention over here 2 electron donor. So this would be replacing one of your COs, and the L would come into picture and CO would be releasing. Similarly, if you have L star as diolefin. Diolefin meaning it is having 4 electrons. Say, for example, this way. So this is a diolefin where we are having 2 double bonds. And now when I'm having a Cp cobalt CO whole 2, and now introducing a ligand L star. This L star is 4 electrons, and these 2 COs are 4 electrons. It would immediately replace this one, making CpCO L star plus 2 CO. So this is where you have to be very careful what electron uh, source and how much electron that ligand is going to give into the reaction, so that you can balance out the whole reaction. Not always one ligand would go out, one CO would go out, or 2 COs would go out. It depends on how many electrons that particular ligand is bringing into the reaction system. To note over here, this reaction can be accelerated by providing a thermal heat or light source. So you can accelerate the reaction kinetics by 2 different conditions: by providing heat thermally, or photochemically by providing a certain light source. Now moving ahead to another reaction where we have a very important feature of cyclopentadienyl metal carbonyl complexes. They undergo oxidative carbonylation, meaning it would undergo the oxidation as well as it would remove your carbonyl group also. So taking a substituted cyclopentadienyl, which is having a substitution of methyl group, this we call as a CP star. It is bound with rhenium and having 3 COs. It is in the group of manganese. It's a 5D element. Firstly, it would be when it would be treated with hydrogen peroxide, that would cause oxidation, which is a 30% weight by weight, and therefore all the 3 COs would be going out because this is an oxidative of decarbonylation. Oxidation of the metal center would happen, as well as carbonyl groups would go out, and we would end up having a product where rhenium is there bonded with 3 oxygens and CP group is attached, right? After that, when you're treating it with PPH3, you already know that PPH3 is phosphorus is having a lone pair and it is also having a good affinity towards the oxygen. So wherever it sees oxygen, it would try to form a p double bond O, pH, and pH that can go out, and ultimately what you will end up having, sorry, a bridged oxygen between 2 rheniums forming a dimer and CP stars onto the terminal side, right? So this is your end product. So this is one of the features of your carbonyl containing half sandwich complexes. Moving ahead, now we are introducing the cyclopentadienyl metal nitrosyl complexes. So let's take that. So our second topic is cyclopentadienyl metal nitrosyl complexes. So here we have two things. That first point is this NO, which is a nitrosyl ligand, it's generally a 3-electron donor. But in linear form, if it binds in a bent form, it acts as a 1-electron donor. So that is there. Therefore, the linear metal nitrosyl group to bent structure MNO, which is metal nitrosyl, this conversion is triggered by, what are the factors which triggers this particular conversion? This triggers by intramolecular transfer of 2 electrons from the metal to the ligand. So this is a factor that triggers particular conversion of MNO linear structure to the bend structure. And if you have upon which a vacant coordination site occurs, because when the ligand has gone from 3 electron to the 1 electron, so therefore there is a tendency of having a 2 electron vacancy. So that creates a vacancy around the coordination sphere that is being generated, and therefore it undergoes associative substitution reaction, because you have created the space without making any particular ligand to leave from that particular coordination sphere, right? There are some other features also of these complexes, which are as follows, that since we know 1 CO is a 2-electron donor, and linear nitrosyl group is a 3-electron donor. Therefore, if you have 3 COs, that would correspond to 2 nitro groups. Both would give you 6 electrons. So if you have 3 COs, they can easily be replaced by 2 nitrosyl groups. Or other way around, that 1 CO replaced by 1 nitrosyl group along with the introduction of a positive charge on the sphere, because when you are introducing an 1 electron extra into the system, it has to balance the charge by introducing a positive charge over there. Moving ahead, there are certain examples. Certain examples of such complexes like chromium nitrosyl 4, Mn, NO, 3CO, C5H5. I was talking about some half sandwich complexes where CO is there, nitro group is also there. So there are many more. So these are certain examples. Now we'll be talking about their preparation. So we have cyclopentadienyl metal nitrosyl complexes, their preparation. So how these complexes are being prepared? Sorry. So how these are prepared? So firstly, we are taking the way we have started with, we have nickel C5H5 whole twice. This is a 20 electron system because nickel would give you 10 electron and 10 electrons are coming from 2 CP rings. When it is been treated with nitrosyl group, since nitrosyl, if it is binding with 3 electrons, it would give you linearly, if it is binding, it would give you 3 electrons. That means uh, if one CP group is going to be replaced by an NO group, so there is a loss of 2 electrons, and that would even make a stable complex of 18 valence electrons. Therefore, it is going to reduce C5H5, or we can write as 1 by 2, half a molecule of C10H10, making nickel C5H5 this side and 1 NO. Now, this is an 18 valence electron. This is a 20 valence electron. Certain other examples are when we are treating with C5H5 cobalt CO whole 2. So this is your half sandwich complex. The earlier one was sandwich complex where both the ligands were CP group only. Now here we know when we are treating with NO, how many NOs are required. Say for example, when I'm treating with 2 molecules of C5H5CO whole carbonyl whole 2, and I'm treating with 2 nitrosyls, 1 CO is being replaced by 1 NO with a positive charge coming onto the coordination sphere. So here we have 4 COs and 2 NOs would give you 6 electrons and 4 COs are 8 electrons. So how it is going to be balanced? It would form a dimer where C5H5 group is there onto cobalt having NO as a bridging ligand with a dimeric formation. Moving ahead, another example that we have is when we are treating rhenium complex having 3 carbonyl groups and treating it with NO positive and NHSO4 negative itself in DCM. So we are going to replace this CO with NO because since we are having 1 NO, so 1 NO positive is 2 electrons. It would replace 1 CO ligand, sorry, 1 CO ligand. So ultimately we will end up having C5H5 rhenium, carbonyl 2, NO, and whole coordination sphere is having a positive charge, and HSO4 negative is outside. So this is a full complex stabilized by HSO4 negative, that is an ion. Moving ahead, we have the structure. That is very important. So the structure of these complexes. So as I mentioned, that NO can be can bind as a terminal ligand, or it can bind as a bridging ligand, just like carbonyl group. So both linear as well as bent structures are possible. So this particular ligand, as I mentioned already, that it can easily bind in a linear fashion as well as the bent fashion, depending upon how many electrons it is going to provide to the metal or it is going to accept from the ligand. So you have to be very, very careful. Now we'll look into the bonding angle and bonding distances properties of these complexes. So one such example that I'm taking is a dimeric system where we have two chromiums bonded with each other with a single bond having nitro group in a bridged fashion. As I mentioned, it can be either terminal as well as bridged one. So in this particular example, we are having both scenarios where it is binding in a linear fashion as well as in a bent fashion along with your CP groups, as it is a half sandwiched complex. One second. Okay, so here the yellow ones are the bridged ones and the red ones are your terminal ones, right? Now, if you'll see carefully, I'll highlight the distances and the angles in white color. So the distance between NO of a bent one or the terminal one is 118 picometer, and the distance of chromium or the bond length of the chromium and nitrogen of this terminal one is 169 picometer. Whereas if we talk about the bridged one, that is bit more elongated, that is a 196 picometer, and similarly here as 119 picometer, which is not much difference, but yeah, the distance between the metal center and the nitro group, the nitrogen has been increased, and the bond angle of NO is 176 degrees. The NO bond angle, chromium NO bond angle. Okay. Now we have certain frequencies. If we are talking about a nitrosonium ion, which is a free ligand, this would be having a frequency of NO frequency of 2250 centimeter inverse. It requires a lot of energy to break that bond. Then we have a NO free. So the frequency has been decreased to 1876. Now, if I'm talking about a linear frequency, that will be 1677, and the bent one is easy to be removed. So less energy is required of the bridged one. So it becomes 1518 centimeter inverse. So these are a bit important frequency values that you should be aware of, or else you should be knowing the nature, whether it is going from a descending order or the ascending order. The NO positive free would be having more frequency, followed by NO, then followed by linear and bridged one. Another such example that we can take for is ruthenium, where we have NO, and here we are talking about both bent as well as linear. So here I'm highlighting this bent one as a nitro group with the angle between ruthenium and NO is 138 degrees. Whereas when we have ruthenium NO, that angle is 178, almost linear, which is 180 degrees. So you have to be careful when you're looking into the angles of it. Followed by that, we have bond distances, which is NO 117 picometer, and this The bond distances is more or less similar because it's a bond distance between nitrogen and oxygen. The main feature that is going to be changed is your bond angle between your metal center, nitrogen and oxygen, where 138 degrees is in bent form and 180 degrees or almost 178 degrees in linear form. So this is where we talked about. In earlier case, we saw the bridged one and the terminal ones. Here we are looking into the linear and bent ones. Based on that, their number of electrons that they are providing to the system, that becomes different. So here also, you have seen the angles and the distances. Now moving ahead with the properties, further properties of it. So now we are introducing cyclopentadienyl metal hydride complexes. So these are another type of half sandwich complex where we have earlier seen carbonyl group, nitrosyl group. Now we are talking about the hydride groups. So here we have these kind of complexes have been mainly observed in 4D and 5D metals. And the 3D metals, in case of 3D metals, they dimerize with the loss of hydrogen. So general examples that we have is that Cp2, zirconium H2. It can be X, where it either can be dimer or anything else. Cp2, niobium H3, Cp2, rhenium hydride, Cp2, technetium H, etc. So let's see the preparation method. Preparation of these complexes. So we are taking a molybdenum Cl5, like simple molybdenum chloride. When it is being treated with sodium C5H5, as you know that it would form your positive and minus Cp group, and in presence of a reducing agent, sodium borohydride, we have used a solvent which is THF in minus 78 degrees temperature, because it could be an exothermic reaction. Now here we will be having a C5H5. So two C5H5 molecules would be bound with the molybdenum. And due to the borohydride group, we have a hydride formation as well. The stabilizer is at 65 degrees Celsius. Moving. Just a second. Sorry. Okay. So next one that we have is, if you are treating rhenium chloride with sodium C5H5, THF, it would easily form C5H5 whole twice, rhenium hydride. So this particular complex is having certain features that are very important to be highlighted here, that it is a air stable complex and it's diamagnetic in nature. If you compare it with Cp2 rhenium, its chemical shift is 3.64 ppm for 10 protons of Cp, and the delta 1H for rhenium hydride is 23 minus 23.5 for rhenium H. This hydride is minus 23.5 ppm. So this has been used for one of the first application of proton NMR in organometallic chemistry. So this complex has been used in that particular system. So how their structure looks like. So their structures are little tilted, the Cp groups, the hydride, as well as molybdenum, which will form two hydrides So these are called filtered CP rings in these hydride complexes. Moving ahead with their certain different reactivity. So if I have a substituted cyclopentadienyl, meaning having a pentamethyl group with rhenium double bonded O, having Cl and Cl. When I'm treating it with first lithium aluminum hydride, which is a very strong hydride source, and methanol, it would end up forming hydrides, 6 hydrides with rhenium and having a CP group. So this is rhenium 7, which is having a tendency to accept large number of hydride ligands. Say, for example, rhenium H6, H7, H9. So this is the property of these complexes. So there are certain characteristics of these complexes regarding the NMR. First point is the proton NMR of hydride ligands. They show separate signals for equatorial and axial protons at minus 90 degrees, but at 60 degrees, which is a little elevated temperature from the room temperature, pulsates occurs, meaning both equatorial and axial protons rapid exchange happens. So that instrument takes an average environment and therefore it gives you a one signal, and none of the equatorial or axial would be determined separately. So these are certain properties that you need to be careful. Depending on the temperature, your spectrum is going to be looking like differently. Also, we have certain features. Lewis basicity of the central metal, that how much less basic it is, that decides the reactivity of these complexes. Say, for example, we have C5H5 whole twice, manganese H2, sorry, MH2. If we are giving a proton source, it is prone to protonation, making a MH3 positive, where M is molybdenum or tungsten. If I am taking rhenium, if you're giving back direction base source, it would take up the proton, and here it would end up forming C5H5 whole twice, rhenium H2 positive. So, depending upon that, the protonation happens a bit faster, how the Lewis basicity is there. And based on that, we are on to our next or last topic, which is certain examples of hydride complexes. And one such example is Schwarz complex. So we have one CP2 zirconium complex, which is Cl and H. This is known as Schwarz reagent. This is a mixed CP metal chloride and hydride complex. So we have so far seen the sandwich complex, uh, half sandwich complex. It's a mix of CP. It's having chloride as well as hydride also. So this is one such example. And this region is very interesting because when you are treating this particular structure or this particular complex with cyclohexene, you have a one double bond. So this point that I'm highlighting over here, A and B, this double bond, it tries to have a hydroxyl correlation reaction where one side of the double bond would be connecting with the zirconium and other side would be connecting with the hydrogen. So we end up having zirconium CP group that side, fluorine is as it is, and one bond with another bond would be hydrogen, right? So this is the way you will be ending up having a cyclohexane group formed with the zirconium. When this particular complex, it undergoes different reactions. We have, say for example, zirconium, CP, CP, the backside chlorine, and a cyclohexane group at the front side. Now, when this reaction undergoes a treatment with D2O, it would release your deuterium substituted cyclohexane group. When it is being treated with oxygen, it would form cyclohexyl alcohol, followed by treatment with bromine to form bromocyclohexane. And this bromocyclohexane, when it is being treated with, and it would release your, so for example, it would release zirconium, CP, CP. One side is chlorine, another side is bromine. And when you are treating it with lithium aluminium hydride, so it would form a hydride, but it would replace the bromine because of the strong bond between zirconium and chloride. So you would end up having this product. So you have to be careful which halide is going to be replaced by the hydride group. Okay. So there is another complex which is your Jordan's cation. Jordan's cation is actually CP2, zirconium, CH3, EHF, whole positive. This is being used for CH activation and CC coupling reactions. So how it is being prepared? We take a CP, zirconium, Cl as Cl. When it is being treated with CH3Li, it would replace the lithium chloride. It would replace the chlorine with the two methyl groups. So we have CP, CP, CH3, the back and front of the plane. Then when we are treating it with NBr3, it would release the CH4 and one molecule. We are treating it with HN butyl 3 positive and BPH4 negative. In THF, release this one, and ultimately it would form CP, CP. THF molecule would bind with your zirconium, as well as one CH2 would remain as it is, making a Jordan's complex. So these kind of complex, the Jordan ones, CP2, zirconium, are ligand positive, or CP2, zirconium, are these type of complexes, these are strong Lewis acids. So for example, if I'm treating Cp2, zirconium, R, L with BF4, since it's a Lewis acid, it would react with the F minus. And when F minus comes into picture, zirconium ligand will go out, F would come inside, and the charge is gone. So BF3 would be released and L would be gone. So this is 0. So these are two particular examples of Jordan's as well as a Schwartz reagent having both hydride and halide into the picture. There is certain reactivity of this Jordan's cation, CH3 THF, which is a solvent molecule, this positive charge, when it is being treated with an alkyne, it would undergo the transfer of reaction because it's a Lewis acid. The double bond would react onto your zirconium, the charge, and CH3 would go and bind with your one side of alkene and having THF over here and the positive charge. So this is the coordination insertion reactions. When you're treating it with carbonyl, again you have a coordination insertion. Cp2, zirconium, it would form C2 bond OCH3, THF, positive. When you're treating it with N times alkene, it would end up forming an alkane with N number polymeric chain with positive charge. It also does sigma bond metathesis with alkanes. We have Cp2, zirconium, CH3, L can be any solvent or neutral molecule. When it is being treated with RH, what it forms really, Cp2, zirconium, it would start making a bond with R and RH bond starts breaking up. The bond between zirconium and CH3 starts breaking and it starts making algist. So whichever it is going to make, I'm just going to highlight it in green color and the other ones are in green. Positive charges there. There is ligand. So ultimately it would release this particular CH4 and Cp2, zirconium, R and L, the positive. If L is equals to THF molecule, then it is slow reaction. If L is PME3, then it is a fast reaction. So this is it for today's lecture, that all the basic concepts have been cleared so far. So we will wait for a few more minutes. Once you just revise whatever I have taught you, then we can have a problem session. Just go through whatever we have read so far, so that if there is any problem, any doubt, you can just put your question in the chat box and unmute yourself and ask the question to me directly. So after 2-3 minutes, we'll start the problem session. there is no question, we can move ahead with the problem session. So first question says that identify the incorrect statements in case of the nitrosyl ligands. So first option is NO positive is isoelectronic with CO. We know that NO generally gives you 3 electrons. When there is a positive, meaning it is 2 electron, and therefore it is isoelectronic with CO. That's the right option. We need to find out the incorrect one. NO minus is isoelectronic. This is 4 electrons. That is oxygen 4. That is correct. 1 electron NO ligand forms linear structure with MNO. No, that is wrong. Only 3 electron nitrosyl group that forms a linear structure. NO is a 3 electron donor. That is right. So option 3 is correct, meaning this statement is wrong. Second question is identify the incorrect statements in case of the terminal mode of binding. So carbonyl ligands can form bent MCO, which is wrong actually. They can only form a linear. So the first statement itself is the incorrect option. We can check the other ones also, because there is an option of multiple statements. Carbonyl groups can form linear, that is correct. Nitrosyl can form linear, nitrosyl can form bent. Both, all three are correct except the first one. Now the question number third, cyclopentadienyl metal hydride complexes are generally observed for 3D metal, 4D metals, 5D metals, or alkali metals. So they are generally observed for 4D and 5D because 3D metals will dimerize and they will lose the hydrogen gas, and therefore there won't be any metal hydride, and 45D are much stable. So the option B and D are correct. Here the option C is correct and A is correct in the second question. Now we have question number 4, which is proton spectrum of the following rhenium complex. So you can see we have one type of CH3 over here, protons, and another hydrogen protons, which the hydrides, which are bound with the metal center. So one peak we will get for metal hydride at 60 degrees. 6 different peaks we'll get from metal hydride at -90. 3 different peaks for metal hydride at 60 and one single peak at -170, -90. So that we have already seen that we are not looking into the equatorial and axial. Those will give you a different peaks at -90 because 90 degrees, because we will be having 3 two axial one and 4 different one. So at 60 degrees, both axial and equatorial seems to be having a rapid exchange, and therefore instrument can only take an average environment. Therefore, only one single peak at a 60 degrees Celsius. So option A is correct. Choose the correct statement from the list given below regarding the regarding a metal hydride complex. So we have C5H5 whole twice MH2. When it has been treated with H positive, meaning a proton source, it will undergo for MH3 positive, molybdenum and tungsten. The option says the reaction is not feasible under any circumstances. That is not correct. The reaction is feasible owing to the fact that CP metal hydride complexes are very prone to protonation. Third option is the protonation occurs only in presence of additional base, and the reaction requires high temperature pressures. So what we have seen that there are certain metal hydride complexes, they are very, very prone to the protonation. So this reaction is very feasible. So option B is correct over here. So option B, this we have already seen. Moving ahead to the sixth question, when we have the metal ion that can readily convert the CpMXN to H2O out of the 4, this we have seen is the silver, which can do this reaction very rapidly. Now we are having a question regarding the Schwarz reagent. So we know the Schwarz reagent is a zirconium-based reagent where we are having a halide, hydride, as well as CP group. So it's a zirconium complex. Option A is correct. This was pretty straightforward. Now we have a reactivity of this Schwarz complex with the cyclohexene. As I already mentioned that it would undergo a hydrozirconation where one side of the alkene would attack onto your zirconium and hydride would go and attack onto your other side of the alkene, and it would making a bond like this way. This is having a bond here, and This bond is your hydrogen, and here you are having a CP group. So this is your group. Now, when we are having already a connected uh, cyclohexyl group over here in presence of oxygen, it would give you a OH group connected to your cyclohexyl. And the last question that we have is, when we have a dihalide, we are treating with methyl lithium. Firstly, both the methyl lithium will take up your chlorine, leaving out two chlorides. So it would firstly form CP, CP, CH3, and CH3. Now, followed by, when you're treating it with ferrocenium BPH4, this is a positive, this is negative. When you're treating it with that, CP2Fe positive and BPH4, what did we do is it would easily take out one of your CH3 outside, and one CH3 would go out and forming zirconium CP, CP. One CH3 would stay as it is, and THF would come into picture, forming a positive. This is the Jordan's reagent, and BPH4 minus. So this is your backbone. Right? So this is your end product. This is your Jordan's cation. So with that, our session for today is finished from my end. If there is any doubt or any clarification that you need, you can please let me know. Not just from the today's session, from any of the sessions that we have had so far. I'll be happy to answer your questions. Since this meeting is going to end in next 15 minutes, kindly let me know if there is any doubt. So this entire session would be uploaded onto YouTube, uh, of which the link would be provided to you, as well as all the material, whatever we have discussed so far today.